So let me know if you're here or if I'm in. Julia, Daniel Cartina, other Daniel,
Here.
Livia, Samantha, Julian, Claire's right here, Allison, Lauren, Ramble, the other Samantha, Brienne, Nicole, Cassandra, Annika, Christina, Dekis,
Here.
Alexandra, Annabelle, Mayan, Ariana, Leah. Thank you. So as I indicated last class, I want to start today with seeing if there's any issues with any of the two review questions. You can be quite confident in the fact that probably the first part of the chapter 4 test, when we get that part, will involve predicting products, writing balanced equations. Now that could be formulas with just arrows, or it could be words with just arrows. And the words with just arrows is what Sherry gives you on the bottom of 181 and then into page 182. And that's, again, that's every time she goes to another question, she expects a little more of you. In number 1, it's just balancing and classifying. In number 2, she asks you to go back and classify. In number 3, she gives you formulas, but no products. In number 4, she just gives you names, but no products. So this type of question is likely, okay? Now, some of the ones I won't expect you to do. So for example, I won't give you a metal oxide reacting with a non-metal oxide and expect you to predict the ternary salt. So for example, if this one here, it's a metal oxide and a non-metal oxide, I wouldn't expect you to do that. I probably wouldn't expect you to write the formula of an acid that's produced when a non-metal oxide reacts with water. That involves oxidation states. So for example, let's see if she actually expects that. If she doesn't, that's fine. There's a metal oxide in water, that's fine. Yeah, this one, a non-metal oxide in water. I probably wouldn't expect you to do that. But metal oxides making hydroxides, yes, okay? If I expect you to assign states, I would probably have to give you the solubility table. Right now, I'm leaning towards against that because it's just, I would have had to have given you practice using the solubility table, and that's time we kind of don't have, and it's not really necessary. You'll get more than enough exposure to that when we get to chapter 7, or if you take Chem 12 next year, okay? Whether I'm teaching it or not. So, I don't want to move on to the next section until I'm confident that you guys have exhausted all the possible problems associated with this. Any issues? And if you did have any, let's say you were struggling to balance something for a reaction for which you wrote the formulas. If you're trying to balance something and you can't, but you wrote the formulas, it probably means one of the formulas is wrong. Which is why it's probably even more important to check the answers for these ones, because if you just can't balance something and you check the answer, you might find, okay, I wrote that formula wrong. So obviously, if you wrote a formula wrong, you can't get a mark for a balanced equation because that isn't what happens. And writing formulas is going to become increasingly important, if it isn't already, as we move to the end of chapter 4. Okay? Going once, twice. Okay. Now we're going to 4.4. We're not doing 4.3. If you want to read about redox and oxidation reduction reactions and assigning oxidation states, fine. Okay? But it's not really part of the curriculum in grade 11. Big unit in grade 12, but not grade 11. So I want to begin here. A good bit of this will be review from Science 10. Not so much the Science 10 textbook, but the Science 10 workbook, which in some instances was more rigorous than the textbook, okay? We're gonna do what we did in grade 10, but add to it. And then we're gonna also represent exo and endothermic reactions in actual reaction form. And you'll see we'll do it in 2 ways. But let's start with what you should probably already know. I would probably write in front of energy here, I'd probably write net energy. Okay. And over this, those are exothermic. That's what it means when net energy is released. And this is endothermic. That's when there's a net gain energy. Okay? Just a different way of saying it. So most synthesis reactions are exothermic. Check mark here. And because decomposition reactions are effectively the reverse of synthesis, most decomposition reactions are endothermic. Net energy absorbed. Neutralization reactions are typically exo, as are combustion. All right? Fuels such as natural gas, wood, coal, and gasoline provide us with energy. Did you ever wonder where the energy comes from? Most of it is stored as chemical potential energy that can be converted into heat. And that type of potential energy, chemical potential energy that can be either absorbed or released as heat, is given a special name. It's enthalpy. Okay? Enthalpy is potential energy that can be absorbed or released as heat. It doesn't always have to be heat, but because it often is, that's why we use H to symbolize it, okay? And the net change in chemical potential energy that can be stored or released as heat is what we refer to as delta H. So what I put up as net energy, that's how we're going to represent it, okay? The amount of potential energy available depends on the position of the subatomic particles making up a chemical sample and the composition of the sample. So that, what subatomic particles are we talking about? Well, we're talking about electrons relative to protons. And we're talking about atoms within the molecule that are stuck together. So, because atoms are electrical animals, because there's negative electrons and positive protons, that's why there are chemical bonds. And chemical bonds always have energy associated with them. Anytime two things that attract each other get together and bond, energy is released. Anytime atoms or ions are pulled apart when they're together, that always takes energy. Okay? But because there's always negatives relative to positives, there's always energy associated with chemical species. It's virtually impossible to measure the total amount of potential energy because all forms of matter exert attractive forces on all other forms of matter. So if I wanted to, measure the total amount of chemical potential energy associated with the liquid in this whiteboard cleaner, it's not just the chemical species making up the whiteboard cleaner, it's the interaction of the molecules of the plastic in the bottle next to the whiteboard cleaner. And then added to that, there's the interaction of the molecules in the air around this, and any form of matter that is close to or far away from that. Which means it's virtually impossible to calculate or measure the total amount of potential energy in the chemical system. But we don't care. What we care most about is the change. So when chemical or physical processes occur, there is a change in stored energy. And that change is what we do care about, because it can do work for us. Remember, energy is the ability to do work. We use changes in chemical potential energy to other energy forms to, for example, heat our homes, move our vehicles. Because chemical energy is most commonly converted to heat, we use the symbol delta H to symbolize a change, I would have said a net change, in the energy available as heat. And that capital Greek delta, that triangle, stands for net, final minus initial, okay? Enthalpy is defined as potential energy that can be evolved, that is released, or absorbed as heat. All sorts of processes, both physical and chemical, as you know, we went through, I believe, in chapter 2, have an enthalpy change associated with them. Well, a general change in enthalpy is symbolized as delta H. Specific types of enthalpy changes may be symbolized by adding certain subscripts. So where does the delta H come from? How do we calculate it? Well, generally, delta H equals potential energy of products minus potential energy of reactants. Final minus initial, which is what net always is, okay? So, the potential energy means the energy stored in the system. So, look at this. This actually isn't a chemical change. This is just taking, at first glance, it looks like a decomposition, but it isn't. Because all we're doing is dissolving this in water. But when you add solid potassium hydroxide to water, attractive forces come into play. The negative ends of the water molecules surround the positive ions, wrap them in that little shell we talked about. The positive ends of the water molecules, a hydrogen, wrap the negative ions. And whenever those attractive forces form, potential energy comes down. Whenever attractive forces form, whenever things that want to get next to each other get next to each other, stored energy comes down. So notice there's a negative here. That means the potential energy stored in these things is less than the potential energy stored in these things. Because it's net. So if this is negative, that means the event that's being described is exothermic. Because the amount of energy that's stored in the system has gone down. Where did that energy, that stored energy go? It was released into the environment. So when you put that in water, the solution gets hot. That's because the potential energy that was stored in the water and the solid potassium hydroxide, the stored energy has gone down and it's been released as heat. Okay? So anytime delta H is negative, stored energy has gone down, which means energy has been released in another form into the environment, usually as heat. Now this is a physical event, not a chemical change. We're just dissolving it in water. So when we say heat a solution, That means we're making a solution. This is the energy change associated with that solution form. But it's not a decomposition reaction. This is a chemical reaction. And this is combustion of propane. Notice, again, that it's negative, but also notice the magnitude. Chemical changes involve much more energy than physical changes. And what are we doing? We're burning it. So this is the heat of combustion. And notice it's kilojoules per mole. We'll talk about what that mole actually means when it's next to a balanced equation. Probably won't get to it today, but we will get to it next class. What's going on here? What do we call this event? When solid water becomes liquid water?
Melting.
Melting. To a chemist, that term is called fusion. And we talked about this, again, back in chapter 2, I believe. Notice that delta H is positive here, which makes sense, because we're overcoming attractive forces. Anytime attractive forces are overcome, potential energy goes up. Consider this felt pen. Where has the felt pen got more stored energy? It's not chemical potential energy, it's gravitational. But where's it got more gravitational potential energy? Down there or here? Here. Why? Well, I've overcome attractive forces to get it here. There's more stored energy in it here than it is down there. So anytime attractive forces are overcome, energy has to be put into the system, which means potential energy goes up. Anytime attractive forces increase, potential energy goes down. So the extra potential energy it has up here, as I overcome the attractive force of gravity, when I let this go, it turns into, that potential energy turns into something else. Mechanical energy, sound, a little bit of heat. Okay? Now, those aren't chemical forces, but the idea is the same. Okay? And we're gonna go into this in actually more detail than Sherry does soon. This is another exothermic chemical event. Now, this is a single replacement reaction, but it's often not that specific. You're often not going to see heat of single replacement. But heat of reaction reminds you it's a chemical change, and you might recognize this as the thermite reaction, except both of those should be L instead of S. Now, look at this one, heat of formation. This is a synthesis reaction. But when we see this formation down there, that means the compound we're forming is coming from its elements. So there's no compounds here. Each element in the compound for a heat of formation measurement has to begin in its natural state at room temperature. So calcium's a solid, oxygen's a gas, hydrogen's a gas. When we begin with the elements and synthesize a compound, that's when we write heat of formation. And notice again, as is the case with the vast majority of synthesis, it's exothermic, which means the energy stored in the products is less than the energy in the reactants. And where is that energy gone? They're released into the environment, okay? What is it that caused the enthalpy stored in reactants to differ from that in products? The answer is chemical bonds. Now, oops, I don't know why it does that. I think it's an issue with the motion. Examine each of the equations listed on the previous page. Consider the sign of delta H and determine whether the reactants or products have more stored energy. Well, if delta H is negative, it means the amount of stored energy has gone down. That means excellent. Okay? So if the amount of stored energy in the products has gone down, delta H is negative. That's exothermic. If the amount of potential energy stored in the products has gone up, delta H is positive. That's endothermic. So put a check mark under the side with more enthalpy. So if the reactants have more stored energy than the products, that event will be exothermic. In other words, delta H is negative, because the amount of stored energy in the reactants, when the products formed, it went down. That's why delta H is negative. If the amount of energy stored in the products is more, that means potential energy of products is more than potential energy of reactants, and that's inverse. Okay? So again, this is another way of saying delta H is negative, delta H is positive. Stored energy increased, stored energy decreased. Okay? Different ways of saying the same thing. Dissolving potassium hydroxide. Notice it doesn't say decomposing potassium hydroxide. It just means dissolving it in water. That was excellent, because delta H was negative. Which means in the dissolved form, when those ions are surrounded by the water molecules, there's less stored energy in that system. And that's because more attractive forces have formed. Combustion of propane, excellent. Melting ice, delta H was positive. We had to put more energy in the system to overcome the attractive forces holding the water molecules together in solid phase. Exo. Suppose your work text has fallen off your desk to the floor. When you lift it back to the desktop, you give the text potential energy. Because of the position above the floor, what does that mean? Because you're overcoming attractive forces. Potential energy always goes up when you're overcoming attractive forces. It's not chemical potential, it's gravitational, but it's still always true. The gravitational potential energy your text now has could easily be converted into mechanical as well as sound, should you let it fall, just like my felt pen. In a similar way, the electrons in the atoms of the molecules of any substance have potential energy. Why? Well, because they're here and the nuclei are here. So the fact that the negative electrons are some distance from the nucleus always means every atom has potential energy. If it were not for their high velocity, they would certainly rush towards and smash directly into the nucleus of the atom, much like your work text falling to the floor. By virtue of the position of the negative electrons in an atom relative to the positive nuclei and the other nuclei nearby in a molecule, the electrons and the protons in the nuclei, for that matter, have potential energy. This is called chemical potential energy, bond energy. And normally, the amount of energy stored in a chemical bond is usually how much energy it takes to break a mole of them, okay, usually. But you don't have to know how we calculate. Suffice it to say that each type of chemical bond has a specific amount of energy stored in it. And when chemical changes occur, there's no such thing as an energy neutral chemical change. Every chemical reaction is either exothermic or endothermic, okay? There's no energy neutral chemical event. The bond energy just mentioned is the energy of intramolecular bonds. Intra means inside. So for example, in a water molecule, the intramolecular bonds are these things. But you guys know when I turn the tap on, what comes out, you can see it. Now you can't see water molecules. They're way too small. But if you can see the water, it must mean there's a whole bunch of them stuck together or you couldn't see it. So not only are there intramolecular forces holding the atoms within the molecule together, but there's also what we call intermolecular forces between the molecules. And we're going to learn in chapter 6 that a particularly strong kind of these intermolecular stick water molecules together. We call them hydrogen bonds. Now, what's in the molecule is much stronger than what's between them, but it's all influenced by positives and negatives, okay? The details of intermolecular forces relate to the polarity or lack of polarity of a molecule, the difference between the potential bond energy of reactants and products before and after a chemical or physical change is known as the enthalpy change or delta H value. Net energy stored difference, okay? Now, this little sentence is really why every reaction is exo or endo, okay? And I'm going to temporarily depart from the book to go into this in more detail. I'm going to start with two definitions. One, or descriptions. One for an exothermic chemical change, one for an endothermic chemical change. And then each of those I will draw diagrams to represent on the board, which you won't be able to fit in the space in your work text. Separate sheets of paper will be required. So let's temporarily depart from this. So let's start with a description of an exothermic chemical change. All right? And I might ask you to hearken back to some of the stuff you did in grade 10. So, under the heading of exothermic reactions. If the energy necessary to initiate a chemical change, you guys want help with spelling? There's no SH in initiate. If the energy necessary to initiate a chemical change, and then in brackets write, if the energy necessary to initiate a chemical change, in brackets, that is, break the bonds in the reactants, called what? What do we call the energy necessary to initiate a chemical change? Break the bonds in the reactants. What do we call it?
Activation energy.
Activation energy. So that's what you put in brackets. If the energy necessary to initiate a chemical change, in brackets, that is, break the bonds in the reactants, called activation energy. End brackets. The energy necessary to initiate a chemical change, that is, break the bonds in the reactants, called activation energy, close brackets, and underline these next three words, is less than the energy released when the bonds in the products form, is less than the energy released when the bonds in the products form. And let's stop there for just a sec. Bond breaking always takes energy. So bond breaking is endothermic. That's what you got to do to start a reaction. But bond making is always exothermic. Okay? And we're talking about the scenario where what you get is more than what you spend. If the energy necessary to initiate a chemical change, that is, break the bonds in the reactants, called activation energy, is less than the energy released when the bonds in the products form, comma, the reaction is exothermic. The reaction is exothermic and involves a net release of energy. And involves a net release of energy. Period. And one more sentence. Everybody with me so far? Or you want me to say it up again up to where we are? You guys all with me? So the last sentence is delta H is negative because you get more energy than you spend. Delta H is negative because you get more energy than you spend. So you got to spend energy to break bonds. You get energy back when they form. But if you get back more than you spent, it's extra. It's that simple. So that's an exothermic description. Let's do endo. All we have to do is change a couple words. It's going to start exactly the same way. So this is endo. If the energy necessary to initiate a chemical change, and again in brackets, that is, break the bonds in the reactants, called activation energy. the energy necessary to initiate a chemical change, that is, break the bonds in the reactants, called activation energy, close brackets, is greater than, underline those three words, is greater than the energy released when the bonds in the products form, not less than, greater than, is greater than the energy released when the bonds in the products form. The reaction is endothermic. Maybe you want to underline that too. Underline exothermic in the first one, endo in the second. The reaction is endothermic and requires a net input of energy. The reaction is endothermic and requires a net input of energy. So far, if the energy necessary to initiate a chemical change, that is, break the bonds in the reactants, called activation energy, is greater than the energy released when the bonds in the products form, comma. The reaction is endothermic and requires a net input of energy. Period. And I bet you could finish it now, but I'll dictate it anyway. Delta H is positive. Delta H is positive because you spend more than you get. In other words, it costs more energy to break the bonds in the reactants than you get back when the product bonds form. So once again from the top, for endo, if the energy necessary to initiate a chemical change, that is, break the bonds in the reactants, called activation energy, is greater than the energy released when the bonds in the products form, comma. The reaction is endothermic and requires a net input of energy, period. Delta H is positive because you spend more energy than you get. Now let's hold on to those two descriptions, because now we're going to diagram on the board both exo and endo in a potential energy diagram. This is reminiscent of what was in the workbook last year in Science 10 with a couple of additions, but it's way more than what Sherry gives you. And in keeping with the definition, I want the diagrams we're going to draw to match it exactly. And let's pretend that this is the middle of the board. And this dashed line, you can almost view it as a mirror, because we're going to look at a hypothetical exothermic synthesis reaction, then turn it around and do the hypothetical endothermic decomposition. And the hypothetical reaction that we're doing, let's do A2 plus B2, giving 2AB. Okay? And we're going to diagram A2 like that. So there's just a hypothetical diatomic molecule. And here's another one, B2. And then our 2AB, we're going to represent like this. And because it's exothermic, we're just going to write plus energy over here. And we'll be a lot more detailed in that later on in this section, okay? So, the grade 10 workbook called these energy level diagrams, they're not called potential energy diagrams, okay? We're monitoring the stored energy in the bonds of the reactants and products as the reaction proceeds. So on the vertical axis, it's enthalpy, but that's just stored chemical potential energy that can be released or absorbed as heat. So that's what's here, okay? On the x-axis, it's not really time, it's reaction proceeds. So in other words, the further you go to the right, the more the reaction approaches completion. And my abbreviation for reaction is just RXN. So reaction proceeds. Some textbooks will use the term reactant coordinate. It's the same thing, okay? So first we're gonna do XO. And in an exothermic reaction, the potential energy stored in the reactants begins as relatively hot. So let's put our potential energy of reactants, put them here. Okay. And again, you'll see why I'm doing these little notches there later. Okay, so these are our reactants. And our reactants are going to be A2 and B2. Okay? To get those reactants to react, as is always the case in a chemical reaction, we need activation energy. What does the activation energy do? Usually it's in the form of heat, not always, but what it does is it speeds up the reactant particles. And because they're going faster, they're going to collide more often and with more intensity. And that's what we mean when we say breaking the bonds in the reactants, okay? They have to hit hard enough that the attractive forces that are in them start to break, and the attractive forces of the product start to form, okay? And that requires energy, and that's always symbolized by an uptick in stored energy, okay? Now, the amount of energy it takes to initiate a chemical change, that is, break the bonds in the reactants, that's activation energy. And we often label that or represent it E sub A, okay? For a collision, if you will, to be successful, we have to break bonds in the reactants, but we also have to start bonds in the products forming, okay? And at the point where a collision is successful, where they hit each other in the right way with the right intensity, there's a short-lived, unstable species that we build. It's not a reactant anymore, it's not a product yet. We give it the term activated complex. And it forms at the instant of a successful collision. So that little AC means activated complex. And what does it look like? Well, these are the things we're banging into each other, right? So what the activated complex looks like in our hypothetical diagram would be this. So we've reached the point where we're just breaking bonds in the reactants, and we're just forming bonds in the products. And if we had to give it a formula, it would just be A2B2. That's the activated complex. It's unstable, it's short-lived, but if we don't build that, we don't get products. The potential energy of the activated complex is why there's activation energy. So every chemical species has a potential energy associated with it. The potential energy associated with the activated complex is why there's activation energy, meaning We have to turn these into that for a successful collision. So when we say break the bonds and the reactants, what we're really saying is the energy necessary to generate the activated complex. Okay? That defines the activation energy. Okay? Unless we build that, we don't make progress. Now, bond breaking always takes energy. So if we're on the way up this hill, if what's being absorbed, potential energy is going up, that means what's predominating is bond breaking, or weakening the bonds. But at the point where the product bonds start to form, that always gives energy back. And that happens as soon as we build the activated complex. Because now we're forming bonds. So now we're kind of turning the corner. So the potential energy to the activated complex represents the energy barrier that we have to do. Okay? And once those bonds start to form, now we're on our way down. Because now the bonds and the products are forming, and that always releases energy. So now down here, we have our products, and rather than A2, B2, we've got one AB and another AB. So those things are now these things, right? The energy released when the product bonds form is the difference in potential energy from the activated complex to the products. That's down here. So that is energy released. And remember we said delta equals potential energy of products minus reactants, net energy change. Well, here's the potential energy of the products. And here's the potential energy of the reactants. So that difference is delta H. And because we've got less energy stored in the products, because this is smaller than that, when we go potential energy of products minus potential energy of reactants, that's why delta H is negative. Okay? So let's go back to our description of an exothermic reaction and see if we can match this to the description. If the energy necessary to initiate a chemical change, that is break the bonds in the reactants, called activation energy, is less than the energy released when the bonds and products form, the reaction is exothermic and involves a net release of energy. Delta H is negative because you get more than you spend. Make sense? And if you wanted to be really specific, if the energy necessary to turn reactants into the activated complex, that's what activation energy is. This minus this is activation. This is why there is activation energy. Okay? And we need to build that. Okay? So that's in that direction. That's in the exothermic, the synthesis direction. All we're going to do now is this. Now we're going to turn it around. Now we're going to do the decomposition endo component. Okay? What started out as reactants are now going to be products. What ended as products are now going to be reactants. And because energy is conserved, because it's the reaction in reverse, what we draw here will be the mirror image of that thing. Not only will it be the mirror image, but we have to build the same activated complex because we have to go from here to here. Okay? And that's why I put those little notches there. And actually, I forgot one. Let's pretend that that's exactly at the right height. Yeah, close. So, now I'm starting down here. What were my products are now my reactants. So my reactants now aren't A2 plus B2, they're 2AB. Something else that I should probably mention. In an exothermic event, I'm turning reactants with relatively weak bonds into products with stronger bonds. Bonds that don't have a lot of energy stored in them are strong. And that may seem kind of counterintuitive, but there's not as much energy stored in these because the attractive forces are stronger. Just like there's not as much potential energy in the felt pen down there because gravity's stronger down there. But when attractive forces are weaker, potential energy always goes up. So an exothermic reaction converts relatively weakly bonded products into relatively strongly bonded, weakly bonded reactants into relatively strongly bonded products. Okay? So let's look at what the activation energy for this one is. I gotta build that. So I have to get to the top of the same mountain, if you wanna use that analogy. It's just, I'm starting from a valley. I'm not starting from a plateau. Okay? And the activated complex that I form is the same one. I have to break the bonds between each A and each B atom and reform the bonds between each of the two A's and each of the two B's. So oriented like that, it would look like this. So these were the two bonds that I had, and I gotta start breaking them. And these are the two bonds I have to start to form. So what I broke there and formed, I gotta break what I formed there and form what I broke. And once those bonds start to form, I have a successful collision. But now notice the height of the mountain is the same, but because I started from a valley, look at how high my activation energy is. Indeed, because energy is conserved, what was the energy released when the product bonds formed here is now my activation. It has to be. When the bonds in the products form, I am now producing what I began with in the exothermic period. So, bring it down. It's maybe close enough. So now my products are what my reactants were. So now I have my B2 and A2. And in the same way that those energy labels were reversed over here, what was the activation energy over there is now the energy released when the product bonds form. Delta H is calculated exactly the same way, namely potential energy of products minus potential energy of reactants. But because now the stored energy in the products is more than the stored energy in the reactants, the magnitude of delta H is the same. The size of the energy change is the same, except there has been a net increase in energy that's stored rather than a net decrease. And over there I said you can consider exothermic as turning relatively weakly bonded reactants into strongly bonded products. The exact opposite is here. Endothermic turns relatively strongly bonded reactants that take a lot of energy, whose bonds take a lot of energy to break, into products with relatively weak bonds. And let's review our description of endothermic. See if we can marry it to this value. If the energy necessary to initiate a chemical change, that is break the bonds in the reactants, called activation energy, is greater than the energy released when the bonds in the products form, the reaction is endothermic and requires a net input of energy. Over here, because this is more than this, exothermic keeps himself going. This is more than enough to get these to here. But in an endothermic event, this isn't enough to bring these things to this. So that's why a net input of energy is required. Delta H is positive because you spend more than you get. You always get energy back when product bonds form. You always have to spend it to break it. Which is more and which is less is what exo and endothermicity is all about. I suppose I should have put a x-axis down here. Right? So let's pretend that's completely horizontal. And this would be the reaction procedures. Make sense? Now, if I haven't retired next year, if I'm still teaching Chem 12, we begin with a unit called reaction kinetics. And you're going to see this almost verbatim next year, okay? So don't throw your notes out. That's the reason I did it in detail. All Sherry does, I'm not ragging on her because all she's really caring about here is net energy change. But if you look on the next page, at the top we have endo. There's no mention of activation energy. There's no mention of energy released when bonds in the products form. To me, you have to do that. And what she puts under it is, if the energy absorbed to break bonds is greater than the energy released during bond formation, it's an endothermic reaction. But she hasn't labeled either of those on the graph. She just said reactants, products. There's no energy spent or energy released. Same thing with what's on the bottom, where there's a net drop in stored energy. That's exo, okay? Now, if you look at the quick check on the bottom of 195, you can probably fill this in already, based on the level of detail we went into. Dissolving potassium hydroxide, that's exo, because delta H is negative. Now, that's not a chemical change, but the amount of energy stored in the solution is less than what the solid potassium hydroxide and water had at the beginning. Combustion of propane is definitely exo. Melting ice is endo. And the bottom two are exo. Okay? Make sense? Now, this is not a very long section. What's left in the section, how much time you got on it? Let's start. 15 minutes yet. What's left in the section, can I erase that? It's hard for me to erase it because it is so nicely done. I used to have a board that I could slide back and forth. And and it was a terrible board, because there were notches in it, didn't erase. So I said, can I please have new boards, plural? So they took out the sliding feature. I don't know why, because it was perfect. I could just draw that once, slide the board over, slide it back. Now I gotta draw it every single time I teach for each of my 3 blocks, which sucks. I do it because I'm a consummate professional, but it's like, it is a lot of work. So if you go to page 196, now we talk about something that wasn't mentioned in grade 10. Namely, how do we represent energy changes in chemical reactions? I kind of did it here, rough and dirty, but there's 2 formal ways we do it. One is called the thermochemical equation, and one is called delta H. So we're going to investigate each. So on the top of page 196, thermochemical versus delta H. There are 2 ways to represent the delta H value associated with the balanced chemical equation. A thermochemical equation includes the energy change as an integral part of the equation. In other words, if it's exothermic, you add plus energy on the product side, as if energy was a product. It's not a product, not a chemical species. But we call it thermochemical because we put energy right into the chemical equation. And we don't just write plus energy on the product side. We add how much energy. In other words, the magnitude of delta H. If it's endothermic, we add that amount of energy to the reactant side. So a thermochemical equation includes the energy change as an integral part of the equation. In an endothermic reaction, the energy absorbed by the reactants to form the products appears on the reactant side of the equation as though the energy itself is a reactant. Of course, energy is not a form of matter, so this can't be strictly true. Energy, or enthalpy changes, are extensive properties. The properties depend on the quantity of material you're reacting. So obviously, if I burn like a milliliter of octane, I'm going to get less energy than if I burn a liter. So we can't just write the amount of energy. We have to reference it per amount of the substance we're reacting, or burning, or forming, or decomposing, okay? For this reason, the unit for an enthalpy change is kilojoules per mole. Consequently, if twice as many species react, the magnitude of the enthalpy change should be doubled. In a thermochemical equation, and this is something that some students have trouble wrapping their head around, because it comes right after our discussion of the mole in chapter 3. In a thermochemical equation, the mole in the denominator of the enthalpy unit refers to a mole of the reaction. In other words, when that amount of stuff reacts, then next to that balanced equation, that means when this happens, okay? So when 2 moles of water, liquid water, are decomposed to make 2 moles of hydrogen gas and 1 mole of oxygen gas, that's the amount of energy required. So this per mole means per that equation, okay? When would it not be next to an equation? Well, let's read on. This indicates that 570 kilojoules of energy are required per mole of this reaction. A mole of this reaction involves the decomposition of 2 moles of liquid water to form 2 moles of gaseous hydrogen and 1 mole of oxygen. Consequently, if 1 mole of water was decomposed, the energy requirement would be half as much. So if this is the equation you're looking at, and if you start with only one of these, then this means when this happens. And notice this is half of this, obviously. We don't usually leave fractions in there, but if that's what's going on, this has to be divided in that. Now, when would you see this? Well, sometimes you might see delta H of decomposition, 286 kilojoules per mole. Meaning, if you've got 1 mole of water and you see that number, then that means when a mole of water is decomposed. But when you balance the equation to have all whole numbers, because there's a 2 in front of that, you gotta double that. Now you'll see what I mean by that when Sherry gives us some examples. So this is endothermic. We add energy to the reactant side as if it was a reactant. In an exothermic reaction, the energy released by the reactants as the products are formed appears on the product side. According to what we've learned about bond energy, it should come as no surprise that the equation for the formation of water is simply the reverse of that for the decomposition, including the same magnitude of the heat change. So if we turn that arrow around, notice again, when this is next to a balanced equation, it means when those quantities are involved. Yeah. Well, you can't be, but if we decomposed 1 mole of water, we would get half a mole of oxygen. In other words, instead of 6.02 times 10 to the 23, we get 3.01 times 10 to the 23. Now, we don't believe that halves of molecules react, but we could certainly get half a mole, okay? So if we turn that arrow around, now the 572 kilojoules per mole of this reaction would be on the product side, okay? The energy released by this reaction is exploited in fuel cells. Prototype fuel cell was used in the Apollo spacecrafts. You guys ever see Apollo 13? You ever see that movie? You should. It's a great movie. True story. Apollo 13 was the first Apollo that went to the moon was Apollo 11. I believe 1969. Are we on recess now? Right. Okay. I'll tell you the story. I don't see you till Tuesday. Probably on Google Classroom, I'll read to the end of this section and do those practice problems. And we'll get there eventually, but those make good test questions.
Oh boy.
Anyway.